Okay, I think now it started. So another way to establish the same theorem is that if I do cyclic transformation, dq divided by t. Now this transformation follows a certain path that I will not fix at this moment, and this must be less than 0. Or if I do not a cyclic but just one transformation of with dq dt, let's say from A to B, from a state A to a state B along a certain path, then again this is less equal than the difference of entropy. So this SP minus SA. And this is done along a certain path. Okay. So suppose that, I don't know, this is, for instance, the PB diagram. And I have a state A and state B, and I follow a certain path. And the theorem establishes this relation. Now, as I said last time, equality holds for reversible transformation. That, I remind you, means just that I'm following a sequence of quasi-equilibrium of thermodynamical equilibrium states, whereas the inequality holds true in the case of irreversible and therefore more realistic transformation. Okay. Now, at some point, I will, if you don't remember this theorem, or if you, I mean, it was maybe 4 years ago that you've done this, or 3 years ago, I will just do an exercise afterwards, just to show that this relation indeed is correct, and this is another way to basically to state which is the second principle of thermodynamics. Okay, so at some point I will do an exercise later on. Okay, but now I will assume that this is correct. I will make an exercise later, and anyway, something that you have done a few years ago. Okay, so you maybe remember this theorem. Now, let's talk about now reversible transformation. For reversible transformation, there is a relation between dq divided by t and ds, which is the following. So now I'm talking about reversible transformation. And as I say, let's just say the dq is equal, ds is equal to dq divided by t. Okay, therefore, TdS is equal to dq. Now, from the first principle of thermodynamics, I know that dq is equal to, let's put here also reversible transformation for what concerns the volume. Let's change the change of the volume. So then I take the PdV, that's usual PdV, and it is du. Now let me insert this equation inside here, and then I get that TdS is equal to PdV plus du. Therefore, u is equal to TdS minus PdV. Okay. TdS minus PdV. Now, as you see from this equation, this is a differential, a total differential of a quantity which is a state variable, and therefore this is an exact differential. Okay, so that means that U, so the internal energy, actually can be thought about as a function of two variables, which are S, so the entropy, and the volume. So du is equal to TdS minus PdV. That means that U is a function of S and V, And also I can establish two relations which are the following: that the partial derivative of u with respect to S at fixed volume is equal to the temperature, and the derivative of u with respect to V now at fixed entropy is equal to minus the pressure. Okay? U dV fixed and minus the pressure. Now these two relations are two examples of Maxwell relations. Now we will see many of them. Those two Maxwell relations are for the internal energy when actually the number of particles is fixed. We will generalize these. And as I said before, the internal energy is a function of entropy and volume. And those two relations establish a relation between the partial derivative of the internal energy, temperature, and pressure. Okay, so those two relations are very useful actually, as we will see in a moment. Now, before coming to the exercise, let's see what the second principle of thermodynamics tells us about the what happens when we reach the equilibrium, and actually in which direction equilibrium is fulfilled. So let me make a certain number of examples. What I'm going to obtain is something that you know, of course, but I will do it now using these Maxwell relations. Since we are in thermodynamics, now you are used to deal with boxes with certain volume and certain number of particles, and so this is the usual framework of thermodynamics. So suppose that I have a box here. Let me put separate this box into two pieces, one with volume V1, then I get a different temperature T1, and U1 as internal energy, V2, T2, and U2. And suppose that this separation actually is fixed. So this is fixed. That means that the volumes are the same during the transformation. So let's say that V1 and V2 are constant. You see where the yeah, but so T1, T2, U1, U2, V1, V2 are different, but this separation actually allows for the exchange of heat. Okay. So if you know by experience, of course, that if the two temperatures are different, then at some point I will reach the thermodynamical equilibrium, and you know what happens, that the two temperatures will be the same at some point, you know. But let's derive these. This is a fact from our experience, daily experience. But let's derive these results starting from the second principle of thermodynamics. Okay. Now the total entropy S is equal to S1 plus S2. Remember that the entropy as the internal energy, they are extensive variables. So that means that if I have two systems or n systems, the total entropy or the total internal energy is just the sum of the single system internal energy or entropy. And again, the U, the total U is equal to U1 plus U2. Okay. Now, the variation of delta S and delta U are the following. delta U is equal to 0. Why? So here I do not have any interaction of this system with the environment. Therefore, the variation of the total internal energy is 0, okay? Because the full system, the total system, is isolated. So there's no variation of the total internal energy, okay? Whereas there is a variation of the total entropy, even if the system is isolated, as we will see. And in particular, okay, let me write this, let me just derive this relation. Delta U is actually delta U1 plus delta U2, and this is equal to 0, which tells me that the variation of the internal energy of system 1 must be exactly the opposite as the variation of the internal energy of system 2. Now, the delta S, the total variation of entropy, is delta S1 plus delta S2, okay, which can be written in terms as a variation, well, I can write this differential as the partial derivative of S with respect to U times delta U, no? So this is the partial derivative of S1 with respect to U1 at fixed volume V1 times delta U1. I will comment in a moment why I say V1 here. Delta S2 du2 delta U2 is a fixed volume V2. Why I'm putting here V1, V2? Because as I said before, there was a relation before between internal energy, entropy, and volume, and we say that internal energy is a function of volume and entropy, or entropy is a function of volume and internal energy. So if I do the partial derivative, I have to fix one of the variables and consider the second variable to be constant. So in other words, S is a function of U and volume. I derive with respect to U, and then I have to fix the volume, no, for a partial derivative. Ok, so qua con una sola lavagna devo cancellare spesso. So now let me write here the equation that we, one of the Maxwell equation relation that we wrote before, that was the following: du ds at fixed volume. This was one of the two that we wrote before, that the temperature is the derivative of u with respect to s at fixed volume. So actually what I see here is actually 1 divided by the temperature, right? Because it's just the opposite of this. So then I get delta U1 divided by T1 for this part, and then I have plus delta U2 divided by T2 by using this relation here. Now, delta U1 and delta U2 are not independent. They are one of the opposite of the other one, as we said before. Therefore, from here, I can write that delta S, variation of entropy, is equal to delta U1, which I can collect to 1 divided by T1 minus 1 divided by T2. Okay? Let me see if it's correct. Cancello qua. Now, the full system is isolated. So there's no exchange of particles, no exchange of heat, no exchange of work with the environment. the second principle of thermodynamics tells me that in this situation, the delta S must be larger than 0. Okay, so from the second principle, I know that delta S is larger or equal than 0. Now, if I consider now this equation, that means that delta U1 times 1 divided by T1 minus 1 divided by T2 must be larger or equal than 0. And therefore, if delta U1 is larger than 0, that implies that 1 divided T1 minus 1 divided by T2 must be also larger than 0. No? If I need to have this larger than 0 relation. This one means that T2 must be larger than T1. Okay? T2 is T1. So now what is the result that I'm getting? Is that if delta U is larger than 0, that means that the system 1 is getting energy from the other system. This is okay, but only in the case in which T2 is larger than T1. Okay, this is a trivial result from our daily experience, but it's obtained just from the second principle of thermodynamics. So this is just telling me that if the system 2 has a larger temperature, basically heat flows from 2 towards 1. Okay? It is very trivial as a result, but the nice thing is that it's obtained just from the second principle and from the Maxwell Relations. So it's just an application of what I'm saying, what I said before. Now, what happens, of course, when the system at some point will reach the thermodynamical equilibrium? Well, when I reach the thermodynamical equilibrium, of course, what happens is that T1 will be equal to the T2. Okay, so the two temperatures are equal, and the delta S now is equal to 0. Okay, so I am in a stationary situation in which I have no, the two temperatures are equal, the system is stationary, there's no variation of entropy anymore. I have reached already the maximum of entropy, and that's it. Okay? Let me see if I have to say something more about that. Okay. Now, the situation that we just analyzed is a situation in which we have established the second principle of thermodynamics. Delta S must increase, but this is true for isolated system. Okay, because what we have considered before is a situation in which we have the total system, which was made by two parts, but the total system is itself isolated from the environment. There is no exchange of anything with the environment. So we are in a situation in which we can apply the second principle of thermodynamics in terms of this relation. Okay, so I know if I have an isolated system, the entropy must increase in time. And you know, the only system which can be considered to be fully isolated is just the total universe. Okay, this you know. So there are, of course, systems which are to some extent also isolated, and for which the thermodynamical, so the second principle of thermodynamics can be applied in this form. But actually, the only system is just the universe. Okay. So that means that the way to state the second principle of thermodynamics in this form is actually a little bit, let's say, unrealistic, in the sense that with in normal situation, we will not have a fully isolated system, and then we have to, so to say, find a way to establish the second principle of thermodynamics by considering more realistic situations. Okay, and the way this is done is considering another kind of situation. So here we have that the volume the total volume is constant, and there is no exchange of work. The total internal energy is also constant because there is no exchange of heat. Now we will analyze a little bit different situation, which is more realistic, and which is the following. So now what we will try to do is to establish the second principle again for situation in which delta V is still equal to 0, so fixed volume, and T, the total, so the temperature of the system is also fixed. T fixed. But delta U can be different from 0. This is the typical situation in which we have our system in contact with a reservoir of heat reservoir. Okay, so the system exchange heat with a reservoir. Ok, come l'ho chiamata? Reservoir? Non mi ricordo. No, it's not important, but the role of this reservoir, what is the role of this, is let's say, to provide the necessary heat in order to maintain the temperature of our system to be fixed. Okay. So, for instance, typical reservoir in let's say daily life is the sea. The sea and the water of the sea is used as a reservoir, for instance, for nuclear power plants, right? Because it's a huge system with a huge heat capacity, and therefore it can exchange heat without changing its temperature. Okay, so this is a way to fix the temperature of a body, so to establish a contact with the body and with a much larger body, which will have a much larger heat capacity. Okay. Now we will see that this situation, in this situation, the second principle of thermodynamics is expressed in a slightly different way. So in this case, I cannot talk about the total variation of the entropy that increases. I will talk about another inequality, and by introducing another potential, actually, thermodynamical potential. Indeed, what we do now is to introduce the Helmholtz free energy, So let me remind you that what we wrote before is that du was equal to TdS minus PdV. Okay, so now this is now the starting point. Let's do what is called a Legendre transformation. From this relation, I see that U is a function, as I said before, of entropy and volume. Now, the Legendre transformation allows to change the dependence of our potential, of our function, the depends from the independent variables. No? So a typical example of Legendre transformation in analytical mechanics is the transformation between the Lagrangian and the Hamiltonian, no? As you remember, so that this allows to talk about QQ dot, so position and velocities, if you want, or to talk about P and Q, no? Position and momenta. This was a Legendre transformation. So now we will do the same here to go from a function U that is a function of S and volume to another function, another state variable, which is the Helmholtz free energy, that will be a function of volume and temperature. So what we do is to introduce a quantity A, which by definition is equal to U minus TS. U minus TS. And this quantity here is a state variable. It is extensive. And it is called Helmholtz free energy. Okay, I don't know how familiar are you with this. You can tell me if you have seen it many times or never. Okay, just to never seen. Okay. Now let me take this equation and put a label. We call it 1. And let us differentiate this 1. So dA is equal to, you can see what I'm writing, right? Otherwise you can stop me.
We can see, thank you.
Okay, okay. So dA is equal to du minus TdS minus S dt equal, now du is written here, so this is TdS minus PdV, and this is du, then I have a minus TdS minus S dt. So TdS should go away, therefore you see that TA is minus S dt minus PdV. And as before, you see now that A, so the Helmholtz free energy, is a function, it's a state variable, this is an exact differential, and it is a function of temperature and volume, dt and dV, and also I can find 2 other Maxwell relations. The 2 Maxwell relations that I can derive from here is that if I do the partial derivative of A with respect to temperature, a fixed volume, is minus entropy. And if I do the derivative, partial derivative of A with respect to volume at fixed temperature, is minus the pressure. Let me check it if this is correct. dV T minus pressure. Okay, minus. Okay, good. Now these are two other examples of Maxwell relations again. Okay. And you see here that I obtained what I said before. Before we had a function u, which is a state variable, depending on entropy and volume. And this is the right, well, or if you want, the entropy is a function of u and volume. And this is the correct, let's say, potential to be used when expressing the second principle of thermodynamics for isolated system. Because I can easily fix the total internal energy and the total volume to be constant, as we did before. Now I told you, now let's try to describe a situation which is more realistic, in which the system is actually not isolated, but is in contact with the reservoir, and therefore the temperature is fixed. And you see now that I obtained that result in the sense that now I have a function, A, which is a function of temperature and volume. So then now I can easily fix the temperature and the volume as I did before for the entropy. So I can work now with fixed temperature and fixed volume and describe a situation in which the system, if the volume is constant, is not exchanging work with the environment, but if T is constant, is eventually exchanging it with the environment. Okay? Indeed, this is what we are going to do now. Dunque, now let's start from again the Clausius theorem, that indeed is very important. That was telling me that that ds was larger than dq divided by t. Okay? Che è successo? Ah, okay. Now this means that T ds is larger than dq. Okay, and what is dq from the first principle of thermodynamics? Dq is a dl plus du, where dl is the infinitesimal change of work. Now, the difference between dl and pdv is the difference between, let's say, reversible and irreversible transformation. So dl is more general, as I said last time, okay? So dl can be the pdv in the case in which I have reversible transformation, but let's be more general. Now, this is the u. Now, from this equation, well, actually from this inequality, I see that TdS minus du, TdS minus du is larger equal than dl. Okay. Now, let me write again the Helmholtz free energy. The Helmholtz free energy was the u minus Ts. Therefore, if I'm working at fixed temperature, dA is equal to du minus Tds, right? Because when I do the differential of this quantity, if the temperature is fixed, that is what I'm talking about now, a system with a fixed temperature, du is dA is du minus TdS. So therefore, what I have here is just a minus dA. Okay, so minus dA, so minus the infinitesimal change of internal of free energy, Helmholtz free energy, must be larger, equal than dL. Okay. Now let's make some comments about this relation. So what we are saying here that the temperature is fixed, and we have found that dA is larger, equal than dL. Now, first observation one is that if I have the equality, so for reversible transformation, I have that minus dL is actually equal to dL, which is equal itself to PdV. Because the Clausius theorem, as I said before, is the inequality holds true in the case of irreversible transformation, and the equality holds true for reversible transformation. So now for reversible, I have an equal here, and also dl is equal to PdV. So what this equation is telling me is that the variation of Helmholtz free energy is equal, but from a sign, to the exchange of work. Now, this is basically just the thermodynamical equivalent of the theorem that you have done in mechanics, which is the Teorema delle forze vive, that tells you that the work done by the forces is actually equal to the variation of the kinetic energy. Okay, so this is the analog, but in thermodynamics, because here this is the exchange of work, and the role played by the kinetic energy now is played by the Helmholtz free energy. So the exchange of work between the system and the environment, which means that the system is doing work on the environment, or just the contrary, is just equal with a minus to the variation of the Helmholtz free energy. So in this respect, the variation of how much the free energy can vary, basically establishes also the potential how much work the system can do on the environment. Okay, so let's say that this is the analog of that theorem of mechanics. Now, the second observation that I can do is that if I work with fixed T and fixed volume, now if the volume is fixed, dl is equal to 0. And therefore, what I get is that minus dA is larger, equal than 0, or if you want dA, the variation of dA must be smaller than 0. And for fixed temperature and fixed volume. Now, what I brought here is just the second principle of thermodynamics, but now in the case in which the temperature and the volume are fixed. Okay, the second principle. Okay. So what this equation is telling me is that similarly to the case of isolated system in which I take the entropy and I know that the arrow of time is the direction in which the entropy, the total entropy, is increasing. In the case in which the volume is fixed and the temperature is fixed, the quantity that I have to consider that is establishing which is the direction of time is the Helmholtz free energy. And in particular, a system in these conditions will evolve in time such as to decrease its Helmholtz free energy. Okay? So this is again the second principle of thermodynamics, but it's in another setup, which is more realistic. Okay? Indeed, if you think about, I don't know, also ourselves, the body, so that the human beings, they are not isolated, of course. And indeed, if from, let's say, unlived matter, at some point you create a biological system, there's nothing that tells you, well, it's not very intuitive that the entropy is actually increasing. Actually, this is not the case because the human body is a realization of just the opposite. The entropy is decreasing. But the thing is that we are not isolated. We are more similar to some extent to a situation like this, in which we can continuously exchange heat with some sorts. And what we need to talk about is not the entropy, but the free energy. Okay, the free energy decreases. Good. Now let's see what this way to express the second principle of thermodynamics tells me about a simple system, which is the usual one, the two boxes. But now this time, the volume is fixed, but the temperature is also fixed, and I can exchange heat with an external reservoir of heat. I think I'm doing this exercise and then I will stop for a break, if it is okay for you. Okay. So let's take a system like the one of before. Again, the two boxes. There is someone who is providing me heat in order to fix the temperature. T is fixed. Okay. To fix the temperature, I have to be in contact with the reservoir. Then I have again V1, V2, and suppose now I will have P1 and P2, two different pressures in the two sides of the box. And this is now a structure that can move. Okay, so it's a piston that can move. Now, of course, the total volume is again equal to the variation of the total volume is equal to 0. Now, intuitively, what happens here is that, of course, the piston will move at some point in order to establish equilibrium. We will see in a moment which kind of equilibrium we are talking about in this situation. But now, since this can move, I can have a variation of the volumes. But of course, the total volume will be the same. So delta V is equal to 0, and this is the sum of delta V1 plus delta V2. Now, as before we computed the variation of the entropy, which was the right variable to be used, now we will consider the total variation of the Helmholtz free energy. Because this is the right condition, now the temperature is fixed and the total volume is fixed. And the second principle of thermodynamics tells me that what happens is that the total, the variation of the free energy must be smaller than 0. So the system evolves towards a situation that minimizes the Helmholtz free energy. Okay. Okay, so this is delta A1 plus delta A2, And this again, we use the partial derivative. This is dA1 divided by dV1 at fixed temperature times delta V1 plus dA2 divided by dV2 at fixed temperature as before. Okay. Now remember that we wrote before an equation which was the two Maxwell relations for the free energy that were telling me that these two these two partial derivatives were equal to minus the pressure. Okay, you just have on your notes. So this minus P1 times delta V1 minus P2 times delta V2. Okay. But now, collegio isolato, delta V2 is equal to minus delta V1, and therefore I can write these as P2 minus P1 times delta V1. Ok, let me see if this is correct. Questo è il 3, questo è il 4, P2 meno P1 delta V1. Ok, so what I have now is that the variation of the free energy, the Helmholtz free energy, sorry, this is not U, but this is A, and this is equal to P2 minus P1 times delta V1. Now, from the second principle of thermodynamics, I know that so the delta of the free energy must be smaller than 0 in time. So the system will evolve in such a way to minimize its free energy. Therefore, what I get here is that if, let me see which is the case, if delta V1 is larger than 0, okay, if this is larger than 0, that means that that implies that P1 is larger than P2 in order to have delta A minus negative. It's okay? So if this is positive, this must be negative, and therefore P1 must be larger than P2. So what is telling me is that if the volume of the body, let's say the system in the first side, is increasing, then pressure 1 must be larger than pressure 2, which is a rather intuitive result. Okay, so the gas of the system, the gas with the larger pressure expands. Okay, which is a rather intuitive result. Okay, so the gas with the larger pressure will expand. So the piston will move from the left to the right. And now, of course, this is a very intuitive result, and again is obtained by the second principle of thermodynamics. Okay, so now in this case, the second principle of thermodynamics is telling me that in order to, so the system will evolve in such a way that the pressure, the gas with the larger pressure will expands up to a point in which at equilibrium, when I have equilibrium, as the case of, we analyzed before, in that case equilibrium was reached when delta S is equal to 0. So any variation of entropy is 0 because there is no way to increase further the entropy. Now here I will reach a situation in which delta A is equal to 0, which means that I have reached the minimum of free energy. Okay? And when delta A is equal to 0, that means that P2 is equal to P1. What this relation is telling me that the two systems are in mechanical equilibrium. Equilibrium. Okay. So you see that again, the second principle is providing me a way to see in which direction the system will try to evolve. In this case, so fixed volume, fixed temperature, the system evolves in such a way to minimize the Helmholtz free energy. Okay, and in this specific situation, that means in particular that I will reach mechanical equilibrium, so that the pressures of the two gas of the two bodies here are the same. So now it's 10. I would say that we will stop for 5 minutes in order to take some oxygen and without the mask. Un po' di anni.
Mi sono perso io o qui ci andrebbe un delta A2?
Sì. Ok, no, aspetta, dov'è che stavo? Me lo sono perso io. Comunque delta A uguale B A1, magari mi sono dimenticato di scrivere.
Delta 1, delta 2 è uguale DA1 su DV1,
sì, DA1 su DV1 e questo è delta V1 più DA2 dB2 delta B2.
Ah, ecco.
Me lo sono dimenticato di scriverlo forse, non so. Se l'ho dimenticato, vabbè, aggiungetelo.
Sì, aggiungo. Pensavo di non aver capito.
No, vabbè, quello ci deve essere per forza il differenziale. Può darsi che mi sia dimenticato di scriverlo nella flex. Okay. Vediamo. Maybe I forgot to write something before. Maybe. You can check on your notes. Of course, there was a delta V2. I don't know if it was missing or not. Questo mi sa che sta finendo. Okay, let us introduce maybe this one. Okay, now, so we have seen these quantities at the moment. Internal energy, entropy, Helmholtz free energy. And we said before that U is a function of entropy and volume. And therefore, if you want, also F is a function of U and V. So this was the right quantity that must be maximized for the second principle of thermodynamics at fixed volume and fixed internal energy, which means no exchange with anything, with the environment. 2, we had a function A, which is a function of temperature and volume, and it's called Helmholtz free energy. Now we will introduce another potential. So this is an example of what is called thermodynamical potential. Thermodynamical potential. Why is called thermodynamical potential? For the reason that I was explaining before, since the variation of this potential is equal to the variation of work with a minus. Okay, so it seems like a variation, if you want, of potential energy that is related to the variation of kinetic energy. Now we will introduce another one, which is the Gibbs free energy. Gibbs free energy. The Gibbs free energy is written with this letter G, and by definition, this is A plus P V. So it's the Helmholtz free energy plus pressure times volume. You will see in a moment why this quantity is introduced. Is another Legendre transformation that will allow to again switch from TV now this time to TP, so temperature and pressure. Indeed, dg is equal to dA plus dP V plus PdV. And dA was derived before. It was minus, so those are the Maxwell relation, minus PdV, minus ST, is dA plus VdP plus PdV. And therefore, I have a PdV that can be removed, and dg now is equal to minus S dt plus dp, dp minus S dt. As before, you can notice that this is again a state variable, and it is a function, this time, of pressure and temperature. Pressure and temperature. And of course, as before, there are two Maxwell relations. The derivative of G with respect to pressure at fixed temperature is the volume, and the derivative of G with respect to temperature at fixed pressure is minus entropy. Okay, let me check if this is correct. dg dp t is equal to v, dg dt p is equal to minus s. Okay, those are two other examples of Maxwell relations. Why this is useful, we will see in a moment. This potential, this is another thermodynamical potential called Gibbs free energy, and this time this is used when working at fixed pressure and a fixed temperature. We will see in a moment which is a possible application of, well, how to express, first of all, the second principle of thermodynamics when now the pressure and the temperature are fixed, and which are the consequences of this. Okay? To be complete, let me introduce another one, which actually will not be used in this course. I think that in chemistry they are much more used to that, which is the enthalpy. Just to make a full list of thermodynamical potential, is the Gibbs free energy. The last one is the enthalpy. And I think there's a H here, enthalpy. This is usually indicated with H, and this by definition is U. By definition is U plus PV. Now you can do the usual trick, so make a differential dH is equal to du plus PdV plus VdP. Now du is equal to T ds minus PdV plus PdV plus VdP. Then I can remove this, and you can see that H is a function of entropy and the pressure. And the two Maxwell relations are the following. Derivative of H with respect to S at fixed temperature is equal to the temperature, and the derivative of the enthalpy with respect to the pressure at fixed entropy and the volume. Okay, those are two other Maxwell relations for the enthalpy. However, I will not use. But let me draw a nice scheme for those quantities, which you can find in the book of Wang, which maybe is very useful if you are in the street. You have you don't have your book with yourself, and you want to think about Maxwell relation. I think it's very improbable. It's probably not very common to do that, but in any case. So one writes the following scheme, draw the following scheme, U, A, G, and H. Here we have the two variables, V and T, on which A depends. U depends on V and entropy, and H depends on entropy and pressure, so I have the pressure here. And now there are two arrows, one is here, and the other one is here. So this scheme will actually help in finding out the Maxwell relations. How? The rules are the following. Here we have four state variables, well, or if you want the four potential we have introduced, is the Helmholtz free energy, Gibbs free energy, Enthalpy and internal energy. The two closest other variables are the independent variables on which they depend. So U depends on V and S. A depends on S and P. G depends on P and T, and A depends on B and T. Okay? Now, if you do, so this allows me already to find which are the independent variables. And the other thing is that I can see which are the partial derivative in the following way. Let me take a simple example. So if I want to do the derivative of U with respect to S at fixed volume, I need to follow the arrow and then we get T. Okay, so the derivative of U with respect to S at fixed volume is equal to T. And this provided by the arrow. Ok? Vediamo se questo è l'esempio. Questo è uno. Ok? Now, for instance, if I have to do the derivative of A with respect to volume, for instance, A at fixed temperature, follow the line, but this time I get to walk through the arrow, but in the opposite side with respect to the arrow. And the rule is that I have to add a minus. But it's a pressure, because minus because I'm just going opposite to the direction of the arrow. And okay, you can work out all the other relations. Okay, so if I do the derivative of what? Derivative of A with respect to temperature at fixed volume, A temperature at fixed volume, I have a minus entropy. Okay, that should be correct. Let me check. Dove che stava? Sì, minus entropy. Okay, so you can work out all the Maxwell relation that we derived before by adopting this scheme. Okay, now that we have introduced the Gibbs free energy, we can establish another way to formulate the second principle of thermodynamics, which is the following. So again, the second principle. But now, this time, instead of fixing, so in the first case, we have fixed the internal energy, total internal energy and total volume. In the second case, we fix the total volume and the temperature. Now we fix temperature and pressure. So we have a system which is working in such a way to be in contact with the reservoir that keeps the temperature constant, and with a system, mechanical system, that basically makes the pressure constant. Okay, so it's a, if you want, the analogous of the reservoir, but for what concerns the work, is a supply of work. Now, the second principle in this case can be written as follows. Second principle tells me that the dg must be smaller than 0 when T and P are fixed. So in a system in which the temperature and the pressure are fixed, what the second principle of thermodynamics is telling me is that the system will evolve in such a way to minimize the Gibbs free energy instead of the Helmholtz free energy. Okay. Notice one thing, that I'm mixing up also the nature of the variables I'm fixing, in the sense that in the first case we were fixing two extensive variables, which were the volume and the internal energy. In the second case, we were fixing the temperature and the volume. One of them is extensive, the other one is intensive. Whereas in this case, we are fixing two intensive variables, which are the temperature and the pressure. Okay. So this is particularly useful when we have a system, as we will see in a moment, although it's not really direct, in which we can exchange particles. Okay, this is particularly useful, this potential in this case. To derive the second principle of thermodynamics in this case is actually not very complicated. Let me just see where I am now. Questo è 4. Mi sono perso completamente. Ecco, 5, siamo qua. Now, to derive this result actually is not very difficult, because G was defined to be as A plus PV. Now, if I work with fixed pressure, if P is constant, dG is equal to dA plus PdV, if the pressure is constant, right? But now, before we derived, see before, we say at some point that dA plus PdV, which was our dL, must be smaller than 0 due to the Clausius theorem. And this was also correct. This result is correct if T is fixed. And we derived this when T was fixed, so T was constant. Okay, so that's basically it, in the sense that dA plus PdV is less than 0, therefore dG must be less than 0. Okay. So I have basically added to this assumption that we did before another assumption which concerns the pressure, the fact that the pressure now is constant, and then I get that dG is decreasing in time. Okay, so the system will evolve in such a way to minimize the Gibbs free energy. Let me cosa faccio? Faccio questo o faccio l'esercizio? Let me see what is better to do today. Maybe I do a little exercise, and then if there is still time, I can proceed with this, with the application of this principle. Okay. Let's start from Cialdino. So now those are the three ways to write down the second principle of thermodynamics. These are basically derived from the Clausius theorem. And now I just want to also to make a sort of exercise to be refresh some calculations that you might have done in the past. Let me do a small exercise so to justify the Clausius theorem by using the Cardinal Cycle. Okay, it's something that you have done already probably. So I will actually go very fast. Okay. Okay, so the Cardinal cycle was the following, so that we can refresh also some law like the Adiabatic law and something like that, which could be useful. So the diagram is the PV diagram, and the Cardinal cycle is made out of four branches. There are two isothermal transformation and two adiabatic transformation. So let me make a draw. So this is 1, 2, 3, and 4. The first one is an isothermal with T2. This is T1. This is the way I do the cycle. And the 2, so 1, 2, so let's write it down. 1 to 2 is isothermal. And also 3 to 4. Whereas 2, 3, and 4, 1, they are adiabatic. Okay. Now, what I'm going to see to compute is the heat exchanged in the different paths of this cycle, and I will show that the sum of the heat divided by the temperature is less than 0, which is the Clausius theorem in the integral form. Okay, so to do that, I first need to compute, of course, the heat which is exchanged by our system with the environment. Okay, and to do that, let me remind you one thing. Of course, one thing is the equation of state of the ideal gas, which is the following. Okay, where Kb is the Boltzmann constant. Let me also remind you that U for ideal gas depends on T, just on temperature. So now when I want to compute dQ2, which is the amount of heat that is being exchanged during the first isothermal, so from 1 to 2, this is PdV, and du is equal to 0 because I am on a isothermal, and therefore the energy is not, the internal energy is not changing, because the internal energy is just a function of temperature for ideal gas. Okay. So let me put it here, du is equal to 0 because of that isothermal. Now, from this, it's easy to now compute the total heat, because now this PdV can be written as Kb n T2 divided by volume, and here I get PV Therefore, dQ2 is equal to KB and T2 divided by volume in dV. And therefore, by integrating all over the path from 1 to 2, I get that Q2 is equal to KB and T2 logarithm of V2 divided by V1. Okay. Of course, this is energy which is gained by the system from the environment, because V2, as you can see here, is larger than V1, and therefore this is a positive number. Okay, this is the heat that is taken from the environment by our engine. Now one can compute similarly, calculation are basically just the same, the heat that now is released from my engine and is provided to the source at temperature T1. So Q1, one can follow just basically the same calculation, is KB and T1, and then I have the log of V4 divided by P3. Okay, which this time is negative, because V4 is less than V3, and therefore this is heat released by the system. Okay. Now, from those two relations, I can derive the following result: that if I write the sum, maybe can I remove this formula here? Okay, but anyway, I can derive from here the sum of QI, let's say, divided by KB and TI. Let me write it here. It's better to take the diagram there. More useful. Anyway, what I can get from those two relations is that Q2 divided by N KB T2 plus Q1 divided by N KB T1. Now this is equal to the log. It's a sum of log. Is the log of V2 divided by V1, V4 divided by V3. V2, V4, V1, V3. Just by combining the two equations we wrote before. Now, what I'm going to show in a moment is that this log, well, actually the argument of the log is equal to 1, and therefore this log is equal to 0. Okay? To do that, I need to remember another law, which is useful to refresh, which is the law of adiabatic, that if you want, we can derive later on. So for the adiabatic, I know that TB to gamma minus 1 is constant along the adiabatics, where gamma is the adiabatic index. Okay, gamma is equal to Cp divided by Cv, is the ratio between the heat capacity at constant pressure and the heat capacity at constant volume. Okay. And now I can use this relation for the two adiabatics that I have here, in particular the 2, 3 and the 1, 4. And this relation is telling me that T2, so let's apply this law for the transformation 2, 3. In this case, I get that T2 V2 to the power of gamma minus 1 must be equal to T1 V3 to the power of gamma minus 1. Let me see if this is correct. T2, V2, gamma, T1. Okay, now instead for 4, 1, I get that T1 times V4 to the power of gamma minus 1, T1, V4, gamma minus 1 must be equal to T2, V1, gamma minus 1. Okay. Now I can play a little bit. For instance, I can divide this side by this side, so I can remove T2, I can remove T1, and then I get that V2 divided by V1 by combining these two equations. V2 divided by V1 must be equal to V3 divided by V4. Okay. I just divide this by this and this by this. So you see, therefore, that if I introduce this relation in the logarithm here, I get 1 as an argument of the logarithm, and therefore is 0. So that implies, if I insert this into here, that implies that Q2 divided by NKB2 plus Q1 divided by NKBT1 is actually 0 for a Carnot cycle, okay, because of this. Which also means, let me now remove the diagram because I don't need it anymore. It also means now I can, and this 0 can remove the constants, that Q2 divided by T2 plus Q1 divided by T1 is equal to 0. Okay? Remember that Q2 is positive, whereas Q1 is negative, as we said before, because there was a logarithm with the volumes. Okay, in the case of Q1, the volume was smaller after the transformation. Okay. So that means that from this equation, I get that Q2 divided by T2 is equal to minus Q1, or if you want, Q1 absolute value divided by T1. Okay. Now let us define the efficiency of a cycle, and we will arrive at the results that we were talking about before, namely the Clausius theorem, but justified by using the Carnot cycle and the fact that we know, we know that the efficiency of a real machine must be smaller than the efficiency of the Carnot cycle. Okay? So the efficiency is written in terms of 1 minus the heat that is released by the system as an absolute value divided by Q2. Okay, this is the definition of efficiency of an engine. Now for Carnot, just for Carnot, the ratio between Q1 and Q2 is just the ratio between the two temperatures. So this is 1 minus T1 divided by T2, just for Carnot. But we know that in general, for a real machine, the efficiency, let's say real, must be smaller than the efficiency of Carnot. What this is again the second principle of thermodynamics. Okay, which was derived in the first year. And it's another way to express the second principle of thermodynamics, which means that 1 minus Q1 divided by Q2 is an absolute value, must be smaller, equal than 1 minus T1 divided by T2. So now I can remove the 1, the minus, and finally get the following inequality. That Q2, beh, facciamolo bene, dai. Quello lì lo rimuovo, quello lo metto di là. Q1 diviso T1 e Q2 diviso T2 lo metto di là. Okay. So from this, I get that Q2 divided by T2 minus absolute value of Q1 divided by T1 smaller equal to 0. Okay? Or if you want, since we know that the sign of this is a minus, this is also Q2 divided by T2 plus Q1 divided by T1 less than 0. And this is just Clausius. Okay? Now, this is Clausius in the case in which we have just two heat reservoirs with two temperatures, T1 and T2. They can be generalized to this. Okay? It's just the total amount of heat released and gained by the system divided by the temperature. Now, in the case of two sources, I just have 2 Q and 2 temperature. This is the general case. Okay. So the Carnot cycle, the fact that the efficiency of a real machine must be smaller than a Carnot cycle, actually, if you want, provides me another way to prove the Clausius theorem. Actually, historically, it was just the opposite. No? So the Clausius theorem was established before, and then one derives the second principle of thermodynamics in terms of efficiency. Now, since we have just a few minutes left, again, just to refresh your knowledge about thermodynamics, maybe let's just derive the law for the adiabatic transformation that we wrote before. Now, we need to remember these two relations, that Cp minus Cv, this is constant pressure, heat capacity, and this is constant volume, heat capacity. And these are equal to Kb and this one thing that we need to refresh. Then the ratio Cp divided by Cv is gamma, and this is called adiabatic index. Okay. Now, in general, we know that dq is equal to pdv plus du, but for adiabatic, now dq is equal to 0, And therefore, I get that minus PdV is equal to du. Okay? And du, in turn, is equal to Cv dt. Okay, now it's a matter of exercise. You can insert here, instead of the pressure, you can put minus N kV temperature divided by the volume, dV, and this is equal to Cv dt. I can put the temperature here, and then I move it from here. Use this relation and this relation. You do the integral, you see that you have two logs here, log of V and log of T, and you can derive the adiabatic law. You can follow this procedure if you want, blah, 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 and derive that T times V to the gamma minus 1 is equal to constant. Okay, I would stop here because diciamo c'è already there. Dunque siamo arrivati qua. Questo qui l'abbiamo fatto tutto. Oh, so you probably have seen these derivations, right? It's just an exercise at the end of the hour. Okay, bye-bye. See you on Tuesday, I think.
Bye-bye.
Ciao.
Arrivederci.
Arrivederci.